Hey there everyone. As an example of inductance of an inductor, we will take a solenoid. There are different types of inductors, different shapes, but a solenoid is the most used one and is the most popular one in a electric circuit. So we are going to find its inductance. Okay, we learned before that in general the inductance is equal to N, the change in the flux as the current is changing. Okay, so now we need to find the change in the flux in terms of solenoid. Let's look at the solenoid here. The solenoid has a length L and it also has several loops. If a current goes through it like this, so it turns here, goes in and comes out. So if you grab on the solenoid like this, because the current is going in towards you, away from me here, so the magnetic field would be to the left, and that's what's going on. Okay, and now if we want to look at things here in general, we know that phi is just simply equals BA cosine theta, and that's the magnetic flux. Okay, the current changes from I equals to 0, so assume the current at the beginning is equal to 0 and at the end is equal to I, which is its maximum value. Alright, so let's look at the magnetic field. As you can see, the magnetic field is in the center like that, and this is the surface area we are talking about. This is the surface area we're concerned with in the solenoid. So if I want to change its color like that, look, the surface area direction is perpendicular to the surface area, as we know. Okay, look, the magnetic field at the center is going this way and the surface area direction is going this way, so the angle between them is 0. Cosine 0 is what? 1. Alright, so we have delta phi, so delta phi is equal to phi 2 minus phi 1. We're going to assume, as we said, the current I1 for the delta I1 is equal to 0, and I2 is just simply I. So when I1 is equal to 0, then the flux phi1 is also equal to 0 because there is no magnetic field. Okay, so delta phi ends up as phi 2, which is B. So I'm going to say delta phi ends up as BA, not B, BA. Okay, so we need to plug that all information in here for now. So L is equal to N, delta phi is equal to BA divided by I for now, because that's what we end up with. Now for the solenoid, if you remember, the magnetic field is equal to mu naught small n times I. I is the current, okay? N is the number of loops per unit length. So let's say 1, 2, 3, 4, 5, 6. So we have 6 loops divided by L. So N is number of loops, big N, divided by L. Okay, so let's plug in B here. Alright, so L is equal to N, B is equal to mu naught small n I times A divided by I. I with I cancels, and N, small n, is equal N, big N over L. So I'm going to write this down as here. So N mu 0 N over L, okay, times A divided by nothing, because 1, because we cancelled I. Now N times N is N square, so we have N square divided by L mu 0 times A, and this quantity here is known as the inductance of solenoid. N square divided by L mu 0 times A. That's the inductance of a solenoid. Notice here something very important, that the inductance of a solenoid depends on the geometry, like the length, the number of loops, the area. That's the geometry of the inductor itself. It does not depend on current or magnetic field or anything else, because this is an intrinsic property of the solenoid itself, so it doesn't have any external elements in it. So all of these, area, length, number of loops is stuff inside the inductor or the solenoid itself. Okay, all right, let's have this example. In this example, we are looking at a solenoid of 0.7 centimeters in diameter, so R is 0.35. We need to turn it to meters, so times 10 to minus 2 meters. Okay, and its length is given. Length is equal to 2 centimeters, or 2 times 10 to minus 2 meters. Number of loops is 150. And what else? Do we have anything else? No, we need to find the inductance. L is unknown. Okay, so this is the equation we need to find. So L is equal to n squared divided by L times mu 0 times A. Okay, mu 0 should be given to you, and it's equal to 4 pi times 10 to minus 7 Tesla meter per amps. I think we have everything. We just have to apply the equation for L. L is equal to N, it says 150 squared, divided by the length, which is 2 times 10 to minus 2. Mu 0 is 4 pi times 10 to minus 7. And the area of the solenoid, or the coil of each loop in the solenoid, is equal to pi r squared. So pi times 0.35 times 10 to minus 2. Don't forget to square that. So pi r squared. Okay, and if we do this calculation, we will get the inductance is equal to 4.5 or 4.445 times 10 to minus 5 Henry, or you can say it is 0.044 millihenry, and that's a small inductance. And that's it for this one. Thank you.